This is me fresh from India. Right when you come in, they take a photograph of you in the Wien Hall. That's me. And Avram still looks the same. So yeah, also, I mean, a lot has been said already about how great Avram was, also as an advisor and a role model. But let me say a few things. Because also as I reflect back on my career and also as I advise other students, I think I appreciate this more and more, like the complete freedom that I got from Avram. So in fact, like my thesis work and most of my research ended up being in scheduling, which was not in Avram's area. But Avram was always like genuinely curious, and we would meet every week and talk about scheduling, and he would have all these amazing ideas. And we even ended up writing a couple of papers on scheduling. So I mean, yeah, looking back, I think it's like amazing, and I wish I could do more of this. And this really helped me, like develop as a researcher and so on. So thank you, Avram. Okay. So yeah, So let me talk about one of my favorite problems, the Komlós problem. So this is a very simple problem to state. Oops. What is this? Okay, I'll just. Oops. Okay, so here you're given vectors, v1 through vn in some m dimensions. And let's say each vector has unit length. And since this is an ML conference, this will be my only ML buzzword. So let's imagine these are objects and these dimensions are features. Right? So the goal is the following. You want to break these vectors into two parts so that, let's say, red and blue. So if I sum vectors in one part and the remaining in the other part, and if I look at the difference, then they're, or like if I look at these two parts, they're as similar as possible in like every feature or coordinate that you care about, right? So in other words, if you look at the difference of these sums and minimize the L infinity norm, you want to kind of make it as equal as possible. And this again, comes up in a lot of places. I'll talk some about it, but think of it as like you're doing some randomized control trial and you want to break things into two pieces. Not quite. So the coordinate directions, yes. Yes, so people look at all kinds of variants, but we'll focus on coordinate. Good, yeah, good question. So actually, Komlós asked in the 80s already, like how small can you make this if I give you arbitrary vectors? So one way, instead of talking of red and blue and this complicated expression, we can write it more compactly. So instead of red and blue, think of +1 and -1. And instead of vectors, you imagine they're just like columns of a matrix. So really, you're hitting like each column with a +1, -1 entry. And so if you look at A times X, and you want to pick a +1, -1 vector to minimize the infinity norm. So I'll sort of use this notation maybe more often. And this is called the discrepancy of a matrix A. So that's our problem. OK, so what's known? So you want to balance all these different things. You can think, OK, let's do random. Sounds like a good idea. And when you do random, you hit with these root n type things because of standard deviations. And in fact, like even if you had one-dimensional vectors, which are numbers, you would get a root n. Now, of course, in one dimensions, you can be smarter. But already, like if you haven't seen this, even if I give you two-dimensional vectors, it's not immediately obvious like how to beat random. Like if you try to balance the first coordinate, maybe the second one gets messed up and so on, right? So OK, so root n is a benchmark. Like root n you can always do. And again, when I say root n, I might ignore like log factors. Like who cares, right? OK, so there was this amazing result like developed during the 80s. There was this whole technology developed, which says you can do exponentially better. So by Spencer and like independently by Gluskin in USSR. So you can get like log n discrepancy or this gap. And this probably, if you haven't seen this before, should look very surprising to you. Like how can you beat random and so dramatically? And it is actually surprising. So these methods are like very non-trivial. They use lattice-based ideas and like pigeonhole and probability. And in fact, just to give you a sense of the complication, like the first polynomial time algorithms only appeared like about 30 years later before these techniques were developed. So this is really something non-trivial going on. But it's like beautiful ideas. And then this was even refined further to root log n by Banaszczyk using even more like sophisticated ideas from convex geometry. And so what is Komlós's problem? So he says, can you always get constant? And constants is the best, right? If you just have one vector, I mean, you have to put it on one side and can't beat constant. OK, so it's like even if I give you infinite dimensions, infinite vectors, can you like balance them perfectly? So that's Komlós conjecture. Okay, and it's still open even after this talk. And actually, so there is no consensus on this problem, or maybe I should say the results I'll show now maybe tilt it in one way. But until recently, like people believed, answer could go either way. So in fact, back as 88, people had conjectured based on some estimates in convex geometry that maybe root log n is the best answer. And just to give you a sense, that root log n comes because if you have like n Gaussians, the maximum is root log n, right? Like standard Gaussian. So that's somehow related to this. But the best lower bound people could come up with was only a constant. And this is even quite recent. Okay, and just a slightly broader context. So you might think, okay, it's maybe a tailored problem. Why do you want to break things in two parts? But there is this whole area of like discrepancy. So you can look at sort of any matrix A. So our Komlós setting is when these matrix A, the columns are of unit length, but you can look at any matrix. And you can define this quantity called the discrepancy. And surprisingly, like, it's connected to a lot of things in somewhat often complicated, like, yeah?
Aren't you missing, like, in the discrepancy, the normalization factor of dividing by?
No, yeah.
So I'm missing something. So, like, what the trivial example if I have the standard unit vectors?
Right.
So you will get something.
No, but it's infinity norm, right? If it was the L2 norm, then it's root.
Okay.
Yeah.
Okay. I knew I missed something.
Okay.
Thanks a lot.
Great. Good. Okay. Yeah. So in fact, there was like a beautiful book by Banaszczyk, like about 25 years ago, called the discrepancy method, where he shows like it surprisingly connects to like all kinds of amazing, topics we all know about in amazing ways. And there was also another, maybe slightly less known book by Yuri Matuszek, also about 25 years ago, where he shows like various applications to geometry. And actually, since that time, these are the most recent books on this topic, and there's been a lot more connections emerging. Okay, so I won't go much into the applications. I mean, that'll be a different talk. So that's my whole spiel about discrepancy. And so in computer science, when you apply these things, usually things are more discrete. And indeed, like combinatorialists have looked at discrepancy. So I'll sort of use that terminology to keep things simple. So you can think of this A as consisting of like 0, 1 entries. Right, so think of it as like you have a set system, and this is the incidence matrix of some set system. So your columns correspond to elements and rows to sets. Maybe here's a toy picture. And now you want to color these elements red or blue. So like hit these columns with +1 or -1. And you want to balance each set, right? And the most imbalance is the discrepancy. Right? So this is typically how it shows up in CS. So I hope the definition makes sense. Okay, and this actually, so if you look at the Komlós setting, this was studied independently by like combinatorialists, Beck-Fiala, back in the 80s. So I'll kind of focus on this special case of Komlós. So let me just like state what this is. So again, you're given a m by n matrix, now with 0, 1 entries. And I want to kind of normalize the column length, right? So we'll say it's k column sparse. So the L2 norm of a column is root k. So it's just a 1 over root k scaling of Komlós. So what's known about this problem? So again, if you do a random coloring, because a row could, so I only have like column sparsity constraint, right? Rows could have like n ones in them or whatever. So random coloring would like hit you with root n right away. But what Beck and Fiala already showed in 81 is that you can get a k, like just so independent of n. And they conjectured root k, which in like Komlós's world would correspond to a constant because this root k scaling. And again, the Spencer and Banaszczyk things correspondingly scale by root k. So that's the state of the art. Okay, so what do we show? So we, in this recent work with Houthi and Jiang, we could manage to improve the Komlós bound to like 4th root of log n, possibly hiding some log factor. So this O tilde is this, but like going below the root log n. And this immediately implies this bound for Beck-Fiala. And in fact, for Beck-Fiala, we can do a bit better because of this special 0-1 structure. So we can actually prove the conjecture and get a root k without any logs. If k was like moderately large, bigger than log square. And previously, it was known for a very narrow regime. And for the full regime, like arbitrary k, we can get roughly, we'll lose some additive root log n and some log factors. Right? So sort of, basically, there's an improvement in the full regime. Okay, maybe I should say, yeah. So the reason why we are stuck at this is because of this additive term. So if somebody could improve this, that would sort of imply the Komlós improvement for Komlós. Okay, so those are the results, and I want to give you. Okay, and maybe other thing, yeah. So all our results are sort of algorithmic, and they run in polynomial time. And the reason I say this is if you look at these previous methods that I mentioned, like somehow, for some mysterious coincidence, they were like existentially. They showed you the existence of good coloring, but didn't give you like polynomial time algorithms based on the methods they use. And in the last, again, 10, 15 years, there's been like a remarkable progress in making both of these methods like algorithmic in like various different ways now. It's become a whole area by itself. So I want to highlight one particular result which we'll be building on. So for this Banaszczyk's version, the root log n, which was like a refinement of partial coloring. So the first result which matched Banaszczyk's root log n for Komlós was by myself, Dadush and Garg in 2014. And again, there will be like several other proofs, kind of generalizing it or using different techniques. Also one with Santosh here. Yeah, so I'll be building on like this work here. Okay, and my goal in this talk is to like give you a general flavor of sort of the previous techniques. And I think the ideas in these are like very clean, and so I'll sort of give you the main idea. And then we'll see why we are kind of stuck, and then motivate the new ideas. And I'll give you like a sketch of, like this special case for Beck-Fiala when k is, let's say, bigger than log cube, how you can improve this like root log to a log log. So that's the plan. And how much time do I have? Maybe I should. Okay, perfect. Thanks. Okay, good. So let's set up. You can forget the whole story, what I told you, and let's just focus on the problem. So you're given a m by n matrix, 0, 1 matrix with k column sparsity. So here is one like standard trick in the area. You can assume that like this m is at least n, and then you can add like empty columns and assume m is equal to n or whatever, like some cheap hacks. So basically, you can think of this as a square matrix. And there is a cheap way to do this. Those of you who know, let me not get onto that. Basically, like if you have many more degrees of freedom than the constraints, you can first solve a linear system, sort of reduce it. Okay, but let's say it's a square matrix. So it's a cheap trick, but it immediately buys you something very important. So you can kind of translate column sparsity of k to like average row sparsity. Right? So why is that? And again, it's a totally trivial argument, but we'll use this again and again. So let's go over it. So, so if you look at the total number of ones in this matrix, it's n times at k at most. But m is at least n, so just by averaging. This stupid idea will come again and again in various disguises. Okay, so let me call, but of course some rows could be very large, like n, right? So let me call a row large if it's slightly bigger than average, let's say more than 10k. And the key point is by Markov, there can be at most n over 10 such rows. So totally trivial at this point. Okay, and if you think about it, like these large rows are the ones that are problematic, right? They're delicate. Like if your coloring was not careful, they can get messed up. And indeed, like if you lived in a world where there were no large rows, so every row was less than like size 10k, you trivially have Beck-Fiala result. Any coloring, color everything 1 gives you Beck-Fiala. Random coloring gives you root k root log n, just by Chernoff bounds. Standard deviation is root k, and then you take a union bound over the n things. So all the pain is coming because of these large rows. Right? And here was this like amazing insight of Beck-Fiala like 45 years ago, that you can pretend you live in a world where large rows don't exist. These like problematic, delicate creatures are not there. And it was a beautiful idea, which I'll explain in the next slide. And of course, many of you have probably now seen this. There's a beautiful book by Ravi, Lau, and Singh. So it's been developed into this whole technique called iterated rounding. But I think Beck and Fiala were probably the first ones. Do you know? Yeah. So yeah, it's a beautiful idea if you haven't seen before. So let me do that. Let me spend a couple of minutes showing this proof. Okay, and before we do that, so one of these amazing ideas of Beck and Fiala was, so ultimately we want to get a +1 -1 coloring, right? But it's useful to think like fractionally. So maybe geometrically, here's the view. So imagine you have a +1 -1 cube. So each vertex corresponds to some coloring. And so what I'll do is I'll start at like all 0. So like things are perfectly split half. And I'll sort of adapt my coloring inside. And maybe if so like imagine I have a particle moving, and if it reaches the face of the cube, which means something is +1 -1, I'm going to walk there. So I'll do that. And somehow, like being able to walk inside the cube will give you much more flexibility or like room to maneuver. That was the idea. And just to set up some notation, Yeah, so this algorithm will evolve the coloring over time. So x of t will denote the coloring vector at time t. And an important parameter will be like how many variables are still alive. So once a variable reaches here, plus and minus 1, we don't touch it, right? So we keep making progress. So like nt will keep track of alive coordinates, which kind of keeps decreasing over time. And yeah, update at time t is just delta xt. And okay, so this update of coloring is happening in this like x space, coloring space, but that induces a discrepancy, right? Like the thing that you care about. So I'll denote a times xt by dt, which is the discrepancy of each row. And like obviously when I update my coloring by delta xt, the discrepancy of row I changes by this amount, which I'll call delta xt. So just to set up some notation. And we want to update xt to keep these things kind of bounded at the end of the day. Okay, so here was the idea of Beck-Fiala. So these large rows are dangerous. Yeah, so okay, maybe as the algorithm goes over time, maybe you have already colored these things to plus minus 1. So these are my alive columns, so the nt of them. And at any time, I'll call a row large if its like support or size on these restricted to these alive columns is more than 10K, right? So it's currently still large. And again, by our averaging argument, there can be at most nt over 10 of those things. So their idea was, oops. Okay, yeah, so what am I doing? Good, so here's the algorithm. So yeah, you have these like at most nt over 10, delicate things. Just walk orthogonal to them. So when you choose your delta xt, just make sure you walk perpendicular to all these large rows. So by definition, you don't add any discrepancy to those. And that's it, and keep doing this, right? And you can always do this because you have nt-free variables, and you're only imposing at most these many constraints. In fact, even if this was like strictly less than nt, you could still find a non-zero direction to walk. So that's it. So the power of linear algebra, and So what does this buy you? Yeah. So like while a row is large, by design it doesn't incur any discrepancy. So if you track like how the discrepancy of a row is evolving, maybe it was very large to begin with, so discrepancy stays 0. And then once it's below 10K, like we lose all control and maybe it goes whatever, but can be at most order K. That's it. So somehow we solve this discrete problem, like going in continuous space and doing something, this orthogonality trick. Okay, so then let me talk about this previous improvement, which matched Banaszczyk's bound. So what was the idea? So again, going back to our previous philosophy, right? If your coloring was random and there were no large rows, you would get this. So if I could combine this, Beck-Fiala trick, pretend there is no large rows in the world, and somehow introduce randomness, maybe I could be home. And so this suggests a natural first algorithm. I still walk in this subspace to protect my large rows, and I walk randomly there. I do some Brownian motion in that subspace or whatever, right? But that is too naive. And the trouble is, I'm forcing you to walk in this subspace. I can introduce like crazy dependencies among coordinates. So let me give you an instructive example. And so the example is really instructive. So suppose, at some time I'm forced to walk in this subspace. Maybe this subspace looks like the following, that in the latter nt over 2 directions, I'm completely flexible. So it's spanned by these basis vectors. But in the first nt over 2 directions, maybe I have this constraint, I can only walk in this direction, so my basis is given by this particular vector. Right, and now this is a problem because any time I sort of walk in the subspace, it's basically saying, all your variables in the direction have to rise or decrease by the same amount, right? So if I had, like some row or a set in the first, maybe which all lied in this, the first K coordinates, if I update things by epsilon, they all go by plus epsilon or minus epsilon, and that's a problem, right? Like you made epsilon change, but your discrepancy increased linearly. And when you see this almost seems fatal. What can I do? Maybe I have no control on which subspace I get. What can I do? So actually, we'll go back to this example, how you can fix this. So what we showed, but first let me tell you the result. So what we showed is, no matter what subspace I'm given, I can still design a random update, so with mean 0, such that no matter which test direction C I look at, so maybe think of C as like 1, 1, 1 on these K coordinates, no matter which direction you look at, like this update looks random for that direction. So let me make that precise. So if you look at c dot delta x, or like summation I ci delta xi, and look at the squared increment, so it almost behaves like these delta xi's were independent, right? So you can write this sum as ci square e delta xi square. So here is a question for the audience. So suppose I was in this scenario though, where my subspace was like badly messed up like this. How can I ensure such a property for every c? Like this seems like in direct conflict. Okay.
I know the answer.
Okay.
You don't walk in that direction.
Exactly. So what you do, you have this crazy dependency. Just don't walk in that direction. Make your delta x 0. Just walk in these other directions, and you would do. Right? You don't have to walk like it everywhere. It just so you can choose your direction smartly. Right? Now, of course, okay, this example we can see by hand and fix it. But turns out, you can prove a general theorem here, and let's even maybe forget what it says. It's basically saying, as long as, if I was in n dimensions or nt dimensions and my subspace wasn't too large, I can basically ensure this independence. Right? Okay, and the way you do it is you write some SDP, which I'll not bother, but you can sort of encode these constraints very cleanly using SDPs, and you can show SDP as a solution using duality. Okay, and so basically you can use this SDP at each step to design your walk. Okay, so here was the BDG algorithm. You do the same thing, protect large rows, but now you use this smart walking, which looks random, to do your walk, right? And you get the best of both worlds. Now, if you, maybe look at the picture. If you tag discrepancy of a row, while it's large, it's incurring 0 discrepancy. Then it's doing some random thing, and Chernow bounds will kick in. You'll get your root k root log n. So that's like a constructive Banaszczyk, right? So we are up to 2016. And if I have 5 more minutes, I can. Okay, great. Okay, so the punchline is you can walk sort of in any subspace randomly while still looking random. So
just to check. So Beck-Fiala, you didn't have to walk randomly. You were walking deterministically in the subspace.
Yes.
And now you're walking randomly in the
That's
subspace.
right. Yeah, that's it. And yeah. Okay, so but walking randomly still loses the root log, and we really want to be more ambitious and even get rid of this guy. So now, so that wasn't clear. So now if you go back to BDG, like there is some obvious deficiency in a sense. Like if you're only blocking large rows, right, like being orthogonal to them, you could also be a bit smarter. You could say, if a row gets too high discrepancy, let me work orthogonal to that. Right? Maybe if I have another NT of them, 10 of them, I can afford to work orthogonal to them. And these ideas have been very useful for various previous problems. Like if you know Lovett-Meca algorithm, this is sort of exactly what they do. But the thing is it sort of breaks down here. And so let me give you like one instructive example why. And this will kind of guide to the next natural idea, and then everything will work out. So this is an instructive example. So let me go a bit slowly over this. So suppose my goal was even to, so let me call this parameter theta. This is what I want to get rid of, or like improve a root log n, but let me even say I want to improve it ever so slightly. So, so that's my target. I don't want discrepancy to exceed this. And let's say we apply this previous idea. So the point is like, large rows are always good. Small rows start doing their thing. And I would expect these many to become bad at some point, right? Because by Chernow, like the chance that a particular row becomes bad is this. And if my theta is like slightly less than root log n, this is already like almost n. Okay, so maybe what can happen is, as I'm coloring my elements, maybe I've colored half of them, but now already like a significant chunk. I mean, it's still n to the 1 minus little o 1, but it's still, they've all become dangerous. They've hit their discrepancy limit. Okay, you might say, it's still good. It's not that many. I still have a lot of free variables. I'm not worried, right? I'll keep going. I like walk orthogonal to all of this. I can afford this. Yeah, no problem. But what can happen, at some point, your NT will fall below this thing. So this width is less than this. Now what? I have to let some people go. I can't protect all these, people who have hit their limits. I can't afford to protect them all. And now what do I do? Okay, so here was the key insight. So let me just say, suppose I could also ensure that if I look at the discrepancy of different rows, that they evolve independently themselves. Now, a priori, this does not make any sense because, I'm picking one delta x, right? How I update my coloring. That determines the discrepancy of every row, like ai dot delta x. So, for example, my rows could be almost identical. So, what do I mean they are independent? They'll almost, vary in the same way. But let's ignore that worry. And one can sort of do a simple argument, which I might skip. But let's believe that in that case, you can do better. Life is good. Everything is random. But yeah, as I said, like rows can this is like it's a pipe dream, right? Like rows could be very dependent. Could be all identical for all you know. So what does it even mean you're dependent? So turns out you can enhance the SDP even more and get this property, and then like everything goes through. So that's sort of the new idea. And maybe let me just quickly sketch. I won't do any proofs. Let me just sketch the key lemma. So good. So let me, So suppose my discrepancy target is still theta root k, but now my theta is like log n, root log n, much more ambitious. So what I'll still be able to show that if this independent evolution was happening, then like with high probability at any given time, at most nt over 10 rows will become dangerous, and which are still like reasonably big. So many rows can become dangerous, but the big, or like maybe I should call them medium, it's bigger. And the point is like if they're smaller than k over log n, then I don't care because like BDG guarantee already takes care of them. So I just need to worry about these intermediate guys between k over log n and k, right? And once you have this property, like it's easy to see because you now just protect these guys and these guys, which you can afford to because of this lemma, and and this is how your discrepancy will evolve, right? So if a row is large, again I don't incur discrepancy because I'm protecting it. Now once it is no longer 10k, that might start incurring, but once it reaches theta root k or dangerous, and it's still bigger than 10b, I still protect it because I can. And now if it's below 10b, I'll let it do its thing, but then it's irrelevant or harmless. Like it's too small to be of any concern to me. Okay, and a simple concentration argument, which I won't do it, shows that if you had these different things evolving independently, like this property is sure. But it may not be independent at all. But turns out, and let me give you one more instructive example. As I said, like we can still ensure that things evolve independently. So let's look at that extreme example, and see how you kill that, and rest is just like quantifying it. So let's look at this extreme case where all my m rows were like identical. This is like as far as independent you can get. But if you're really in this case, this is easy to handle because I just pick my delta x to be this orthogonal to A1. So I just lose one linear constraint, and I kind of get to walk orthogonal to them all. So it's like one blocks all, kind of, right? So you can actually write an SDP to make this idea precise without losing too much. And so kind of you can gain approximate independence. And then the sort of this independent argument can be made to go through. So again, like if you want just like a one-line summary, the point is, it's really the power of SDPs to do like design crazy walks. So you can design these walks. So this was BDG, like for any direction it looks independent, behaves like a random thing. But now like simultaneously the entire discrepancy vector sort of looks like it's evolving. Each of its coordinates is kind of evolving independently. And that buys this extra thing. Okay, and you can sort of, so if you just use this nice naive idea, when k is bigger than log cube n, it already gave you like only log loss. But then it kind of becomes worse if k is small, but you can still extract this, which gives this for Komlós. You can think of Komlós as like a different scales of, Beck-Fiala, different scales of k. And if you go like even more crazy with this idea, use some recursion, you can squeeze out more out of it. You can show this. So in particular, I think this was nice because this exactly gets the Beck-Fiala conjecture for once k is reasonably large. But good, and this is my last slide. So let me just say, so I think, so if I had to put my money, I would think now probably Beck-Fiala and Komlós, probably they are true, or at least you could get log n, right? I mean, this log to the 1/4 seems kind of strange thing. And there is, I think, a very concrete idea, but I don't know how to implement it. So let me just sketch it. So let's go back to this analogy, how we started. Like if we lived in a world where there were no large rows, right? Because that's how we started. And we saw, like random coloring would have given you this. And BDG kind of was inspired by this idea. But actually, you could apply low-Vast local lemma because now, column sparsity is k, row sparsity is like order k, so dependency is like k square. You don't need to lose the Lugan, you can just lose log k there. And if you know what LLL is. But now, we already know Beck-Fiala conjecture for k bigger than log n, so only hard regime is when k is really small, where this concentration breaks. So if I could prove LLL in this, like if I could make this analogy and apply LLL techniques with, by protecting large rows, I would actually get at least this. The problem is, there are various algorithmic techniques for LLL, Mozart-Ardosh, and even going back, but I don't quite know how to combine using this orthogonal idea to walk to orthogonal to big rows, because they are actually there, right? I mean, if they were not there, we can do this. So I have to make them disappear somehow. The only idea them to disappear is orthogonal, and I don't know how to combine existing approaches. But it feels like morally there should be a way, and this probably should have more applications beyond just like this particular problem. Okay, so let me thank here, and thank you, Avram, again for everything, and thanks everybody for your attention.
I mean, all the work on discrepancy started with these probabilistic methods, very non-constructive, until you came up with this idea of SDP.
Yeah.
So in your proof, somehow you're coming up with a constructive algorithm. But if you say, I just want an existential stuff, you don't need the SDP, you can throw anything.
Right.
Could that help?
Yeah, so I don't know of any other way to like improve, Banaszczyk, even if I don't care about polynomial time. Yeah, so this may be another thing, right? Like previously we were just catching up with the mathematicians. It took us 30 years, but now it seems our algorithmic techniques might give beyond like what these guys could do. So I think it's good news for CS. Yeah.
Santosh.
So the last thing you mentioned, is there a chance of a Brownian motion random walk style to achieve LLL?
Yeah, exactly. So that's kind of the question. Yeah, I don't know, because all these things, they do recoloring. Yeah, I don't know, right. Yeah, I would, if I had to bet my money, not crazy, I don't have crazy money, but like, I would put, there should be something very different way of getting LLL. Probably.
So I have another question. Is the reason why you're blocked at that k over log n because you need space in constructing the dual? Like you wanted this independence.
Good. So the k, I kind of went over that, but I chose k over log n because below k over log n, those rows are harmless by BDG. So you can argue that the number of rows that I care about at any time is only nt times log n, again by that naive averaging argument.
I see.
Because column sparsity is k, and I only care about rows which are bigger than k over log n. So there can't be that many. Right? And then again, you plug in that SDP lemma and kind of log n wise independence.
I see. Okay.
And then it's a bit of a parameter fitting, but I can pull this through.
Awesome. So then, thank Nikhil again. And we have a coffee break right now until, do you remember?
11:15.
11:15. So 25 minutes. See you guys back then.